Hi everybody. So just recently I did a repair video on a Yamaha model CR400 stereo receiver. And it had a really interesting feature in the power supply. The amplifier it's a lower end receiver. It's only 16 watts per channel. Nothing fancy, but it really had good specs. It sounded really good. And one of the unique features of it is most low-end amplifiers like that won't have a protection circuit in it for the speakers. So higher-end stereos usually will have that relay. They call it the protect relay. And when it goes into protect mode, the relay disconnects the speakers from the terminals pretty much internally inside the amplifier. And a lot of the lower-end receivers don't have that as a cost savings practice. And if you recall, I did a video on a Kenwood KR710 that had a shorted output transistor, and sure enough, it actually put the full B+ voltage out onto the speaker terminals. And of course, if you had a pair of speakers attached to that, it could really cause some damage. But this was a pretty intuitive little thing that Yamaha did on this one, in that they put this little fuse right here in the return line for the power supply transformer. It goes right to that center tap right there. So if you recall, that fuse had blown. And it got me to thinking, wow, that's really cool. Let's do some experiments to see, number one, how you would rate this fuse. You know, how many amps should this fuse be? And number two, how does it work? How is it that if something fails in our output transistor, so this is just a cutout of the schematic from that CR400. These are your output transistors, your push-pull pair, and you have the positive going voltage going into here, and it goes through a 2 amp fuse. And then you have your negative power supply voltage right here, and it kind of loops around, it goes off the page, but it ends up at the bottom here going into the PNP transistor, into the collector. And this is the center point, and the center point, if you look, will go through the speaker terminals, and then the negative speaker terminal will end up connected to this point right here, or we should say this point right here. And these are those big gray filter capacitors that were in there. Go back and watch the video if you haven't seen what I'm talking about. But I thought, you know, this is really interesting. Let's see how this works. Let's see if we can mock up some sort of just a little circuit on a breadboard to simulate what happens when these transistors drive a signal into the speaker, and what happens to this center tap. What kind of current can we expect here, and how do you think it would work? So that's what we're going to do in this video. Now, the first thing I did was drew up a kind of a simulation circuit that we can build that's very simple to demonstrate how this thing works. And it consists of a power transformer with a center tapped secondary, just like the one from the Yamaha. So you notice there's your center tapped secondary, same thing here. It then goes directly into a full wave bridge rectifier. Okay, so same thing as here. There's your bridge rectifier. And coming out of where the two cathodes are connected of the diodes, that would be your positive voltage, and I'll mark that on here. So this is going to be your positive. We'll call it B+, and B- will be the anodes of these diodes here. And essentially, what we have right now is we're simulating this. We're going to put two resistors in series, and we're going to have, and I mentioned in that video that you have a current loop through this whole circuit. Now these, we'll talk about why these are here later. We'll get to that in a little bit. And then we're going to connect this center tap through an 8 ohm dummy load and refer it back to this center point where these two resistors come together. Okay, I think you already see where we're going with this. Now, what I want to do is, remember, transistors are current controlled devices. So they work with current gain, forward current gain. So what we want to do is we want to measure the current at all of these nodes. So I want to see what the current is at the positive voltage supply, what the current is at the negative voltage supply. So we have 1 amp meter here and 1 amp meter here. And then I also want to see how much current is flowing through that center tap and through our speaker, our dummy load, which would kind of represent our speaker. So we have a 3rd amp meter right here. So we're going to build this circuit. It's very simple. It's going to have a transformer, a bridge rectifier, and 3 resistors. So let's build that, and then we'll be right back. Okay, I had to back the camera off a little bit to get everything in view here. So those of you looking at this on your smartphones are probably suffering right about now. Sorry. But here it is. So here's our schematic. The transformer is right here. And all this is a 16-volt center tapped transformer. So there's from here to here is 8 volts. From here to here is 8 volts. I'll hold this up. So from here to here is 8 volts. From here to here is 8 volts AC, RMS. And from here to here would be 16 volts. So this is a center tap. All right. We're coming out of there and we're going into a bridge rectifier. And this is just a little one I pulled out of a bin, used one. And that represents these 4 diodes here configured in this configuration. I actually have, if I zoom you in for a moment, I actually have 4 resistors on there, but only 2 are connected right now. Notice these other 2, the ends of them don't go to anything, and I just have these jumper wires in there for the moment. All right, more about that later, okay? And those represent the 2 resistors here and here. Let's get you back in frame. Okay. And then when we look here, this is our 8 ohm dummy load resistor. It's way overkill because it's so big, but that's the only 8 ohm resistor I had handy real quick without doing a lot of digging. We also have our 3 amp meters. So the one on the far left here, this meter, we'll turn our little lightsaber on, huh? This left one represents the positive power, or the negative voltage power supply, which is this one down here. The meter on the right is the positive voltage power supply, and that's this meter up here. The one in the middle is the center tap, and that's this point right here on the schematic, and it's measuring the current flowing through the dummy load, or our simulated speaker, into the center tap. So let's turn these all on, and we're going to measure DC amps. All right, because of course when this comes out of here through this rectifier, it's going to be DC. And let me turn the power supply on. Okay, when I power it up, you can see we have 15.7 milliamps on the negative side and 15.7 on the positive side. We essentially have the same current at each of these points right here. And that makes perfect sense, because if you follow this, it's going through the bridge rectifier and it's coming through here, and you can see we have a current loop through this power supply, just like this. So because this is a series circuit. And if you notice, there's really no current flowing right now at all through this 8 ohm load. None. I wonder why that is. It's connected, isn't it? You would think that there would be current flowing through that center tap, but there's not. And if you remember when we did the tests on that CR400, that was very similar to what we saw. Very minimal current flow. All right, so what happens if we were to change these? If you notice, these are both the same resistance. What if I changed one of these to be half of what it is right now? Instead of 4.7K, it's going to be, let's say, 2.35K. So I'm just going to put another 4.7K resistor in parallel with one side. All right, so I'm going to put it on the negative side first. Well, actually, let's put it on the positive side first. We're going to put a 4.7K in parallel with this one, and that will make the effective resistance here 2.35K ohms. All right, so we're going to take this and we're going to jumper it right here. And what happens? When I do that, I have about 16 milliamps here, but I have double that, almost double that here. I have 31, almost 31 milliamps here. And look at that. I have 14 milliamps now flowing through the center tap. How about that? Now, if I take that back off, everything goes back to normal. Let me put it back on again. 14.5. So you can see this side really didn't change hardly at all, did it? All right. Now, what would happen if we did the same thing here? So now this time we're going to leave this at 4.7K, and we're going to add another 4.7 in parallel with this, making this 2.35K. So let's see what happens. So most of you probably can already figure it out. And if you notice, now this side remains the same, but this side almost doubles in current. Again, you have your 14 milliamps, but take a look. We now have a negative sign on there. Negative. So that means the current is flowing in the opposite direction that it was the last on when we put the resistor in parallel on the other side. Interesting, right? Now, here's the real question. Why did the current double on this side? And why did it stay the same on this side? Let's think about that for a second. You know, you can never have too many meters, can you? Let's move this where we can see it. Okay, measuring across this first resistor, which will be on the positive side. If I go from here to here, you can see there's about 7.5 volts roughly. And if I go from here to here, across this resistor, the other side, I'll just leave my negative in the middle where it should be, sorry. I have about negative 8 volts. So I have minus 8 on this side and about 7.8 volts on this other side. So they're just a little bit different, and some of that has to do with the differences in the resistors slightly, and some of that has to do with the meters themselves being a little bit different. Okay, because these have a resistive shunt in them to be able to measure current. That's called a burden voltage. These meters may have a slightly different burden voltage of a couple of millivolts difference. But we won't get into that in this video. And if we look at the total across the whole circuit, I'm trying to hold my plus and minus in the right way, sorry. We have about 13.8 volts. Okay. And remember, I told you this was 16 volt center tapped. Why do you think that is? Well, we're missing a key component, and I did that on purpose. So right now, what you're actually looking at is the RMS value of that voltage. In other words, you're not seeing the full peak of that voltage. So you're really only getting the RMS voltage, which is going to be that reduced amount. And the reason for that is we have one key component missing, and that is our filter capacitors. So if we go back to our original circuit, it comes out of here and it goes down to here, and look at that. There are those two big capacitors, 3300 microfarads. So let's put two capacitors in there to simulate that. Okay, I've now drawn a couple of capacitors into the circuit. And this is what we've done down here on the board. If you notice, we added two capacitors. All right, let's turn it on and see what we get. Now the first thing you notice is the current went up substantially. And if I measure the total output on the circuit now, you now have 23 volts. How about that? Instead of only about 13 or 14, whatever it was. So it went up substantially because of those capacitors, because now the capacitors are charging up almost to the peak voltage of that sine wave, of your AC voltage that's going in there. So we have a lot more solid power supply. Now, same thing if we put our parallel resistor on the positive side. You can see it does the same thing, and we get current into the center tap. And if I go on the other side, it goes to this side, and we get negative current flow in the negative direction. Okay? And watch this. Let's take the center tap all together. Let's take it out. So what I'm going to do now is I am going to remove this center wire right here. And we'll see what happens. Okay. So here's the center wire from the transformer. You can see it. It's been removed. Nothing really changes right now, does it? We still have that same current flow on both sides because our resistors are the same. But watch what happens to the center tap now when I put this other parallel resistor in. Do you see what happened? And then when I take it back off, it goes the opposite. So I have the negative side I'm turning on now. Watch, it'll go negative, and then it'll bleed off until the current remains the same. Then I take it away, and if I connect this center tap back up, let's see if I can do that. Here we go. And now I put and there you go. And you can see even with that there's a little delay as these caps regulate. They come up to their they settle to their charge that they're supposed to be at. Very interesting stuff. So we got an idea of what these two resistors are doing in here. But what if we remove those resistors and replace them with transistors in the same configuration? So instead of these resistors, we would have this PNP transistor going to the negative supply, this NPN transistor going to the positive supply, and then where the two emitters come together at that junction point, we connect that to our center tap. And that's essentially what your push-pull amplifier is doing. So when we drive these, and remember these are current-based devices, so when I turn one on more, one will begin to conduct more current than the other, and there will be less current on the opposite side, which will make a net difference at this center point. That amount of difference will reference itself to the center tap through your speaker load over here. And conversely, if the other side turns on more, then this one will be turning off. And as this one turns off and this one turns on, you have an imbalance in the opposite direction, and you have current flowing in the opposite direction through your speaker once again. And this is how a push-pull amplifier works, and this is how this power supply feeds all that. And this is how the power supply reacts to the change of the loads that you put with respect to the center point. I thought that was really interesting. And if you notice though, even though the current was doubling here when I halved this amount of resistance, and of course Ohm's law would tell you that, wouldn't it? But only half the amount of current was going through here, which was the amount that we changed the difference between these two. And that's why, if you remember on our schematic, these fuses were rated at 2 amps, but this one was only rated at half of an amp. Now, again, we can get into an entire video series about fuses and how they work. But if you do the math, you'll find out that that half amp on a 16 watt amplifier is going to be right about where you're going to want to rate that fuse. So if you run that amplifier at hard clipping for a length of time, that'll be just enough to overload that fuse and open it up. But it won't obliterate the fuse because, again, that half amp fuse can probably take 3 to 4 times that half of an amp for a certain period of time. But the longer you leave it on, the more it'll heat up. It will eventually fail. So that's just right. But if you had a hard short, let's say we dead shorted this resistor right here, which would simulate a shorted transistor, that would cause excessive current to flow very quickly. Now that's going to flow through the speaker naturally, but not long enough for the speaker to blow out, because that filament of that little half amp fuse will fail long before the voice coil of your speaker will fail. The only time that that would be an issue is if you have an excessive DC offset, like you have an offset voltage sitting there and it's not quite enough to blow the fuse. And what will happen is the voice coil in the speaker will get hot, and it will heat up and heat up and heat up, and eventually that will damage the voice coil. So this isn't foolproof, and it certainly isn't as good as an actual relay protected speaker protect circuit, but it is a good poor man's speaker protection circuit. So it does do its job, just not as well as a protect relay. Okay, that wraps it up for this video, and I hope you enjoyed it. I had a lot of fun doing this little experiment and visualizing what's happening inside the push-pull amplifier circuit and why that fuse was rated the way it was. It all works out. It's pretty ingenious when you think about it. It's definitely would have protected that Kenwood amplifier had they put that one little fuse in there. That Kenwood would have still leak that full B+ voltage out to the speaker, but that fuse would have failed much quicker than the speaker connected to the circuit would have failed. And that may have protected the speakers, and that would have also disabled that amplifier so that you can't get an output. Now the other thing is, if you got a short on one of these transistors, that will definitely open this up through the speaker, but in addition, if it's a hard enough short, this 2 amp fuse will fail as well. One of them goes to one channel, one goes to the other. And since it's all referenced, as I showed you, it's all the same in one thing, you only need the fuse to be on one side. It doesn't have to be fused on both sides, because that loop right here is a series circuit. So that's the reason you only need the single, because somebody commented, why did they only put a fuse on the positive rail and not the negative? You don't need it on the negative. Okay, that was a fun little video, and as always, I wish you all peace, joy, happiness, and good health in your lives, and hope to see you again with some more fun on the bench here. All right, you all take care and have a great day. Bye-bye.